My topic today is a qualitative analysis of Android Taint-Analysis result. This is a joint work with my advisor Eric Burden and my colleague Johanna Speth from Fraunhofer IEM. For those of you who are not familiar with static Taint-Analysis, I would like to give a short introduction. Static Taint-Analysis can be used to detect data leaks without executing the program. It tracks data flows between a data source, where sensitive data is read by the program, such as your contact list, to a critical sink, where the data shouldn't be reached, such as a HTTP connection API. We call such data flows between source and sinks the taint flows. Popular taint analysis tools such as AlmondDroid, FlowDroid, and DroidSafe, they consider different sensitivities to improve the analysis precision. A taint analysis is flow sensitive when it is aware of the order of the program statements. It can also be context sensitive when it keeps track of the calling context. Analysis is field sensitive if it models the face of each object, as you can see from this example. It can also be object sensitive if the analysis distinguishes the function calls made on different objects. Previous work has considered all these sensitivities. However, to the best of my knowledge, state-of-the-art taint analysis are not path sensitive, which means they don't take the execution path into account. As you can see from this example here, static taint analysis tools will tell you that there is a taint flow between the source and sink, which means this is a potential data leak. However, they won't tell you that which value does actually the variable secret hold at runtime. Maybe it doesn't hold a sensitive value at all. And also they won't tell you that this taint flow can only happen when the command read from a file is equal to upload. So this taint flows is potentially false positive. Researchers have proposed using dynamic analysis to validate static findings. Dynamic analysis, they monitor concrete execution and they can extract runtime values. However, dynamic analysis tools must run a test case which covers the execution path. In this example, the test case needs to provide a file which contains a string which is equal to upload. This path condition in this particular example may be easy to be satisfied. However, what about this one? As we can see here, there are m plus n conditions needs to be satisfied for generating a test case which execute the source and the sink statement. Obviously, it is hard to generate such a test case. In the last slide, you have seen an extreme case. However, we don't know if such cases are actually common when considering taint flows in real-world applications. Thus, we would like to study Android taint analysis result on real-world apps. Our goal was to understand what kind of path conditions are actually relevant to the taint flows, and how taint flows are conditioned on different factors. More precisely, we would like to classify taint flows which are dependent on different factors. Since it is impossible to study all path conditions, we define three factors we would like to look at. These factors were often mentioned in previous literature. In particular, we seek to identify how taint flows are conditioned on I/O operations such as file reading and writing. As you can see from this example, this is interesting to study since it is often difficult to track such cases dynamically. Secondly, we would like to identify how taint flows are dependent on UI interactions. since Android provides a rich set of user interfaces. Thirdly, because Android apps are highly configurable, so we would like to understand how Taint flows are related to this configuration, such as environment settings, such as platform version or internet connectivity, and so on. In our study, we choose Floudroid as our study object since it is one of the most popular Taint analysis tools for Android, and it is well maintained. In our study, we proposed a few research questions we would like to answer. Due to time constraints, in this talk, I will only answer the following two questions. So the first one is, what types of Taint flows does Floudroid report regarding the three factors we define, and how common is each type? However, there were some challenges to achieve our research goal. We couldn't simply extend the underlying Taint analysis of Floudroid to make it path sensitive, since this would bring a scalability challenge for the real-world application, so Floudroid may not scale. In addition, analysis of path constraints is actually a non-distributive problem, because the execution of a branch may simultaneously depend on two or more values. Moreover, Floudroid was built on top of the IFDS framework, which actually only solves distributed problems. Our solution to solve the problem is as follows. Instead of extending Floudroid, we implemented a standalone tool called COVA, which can be configured to check the path conditions that depended on some predefined APIs we call constraint APIs. And COVA computes a constraint map for each reachable statement. We analyze the Android app with both with Floudroid and COVA separately, and then we merge the result of both afterwards, such that each Taint flow reported by Floudroid is labeled with a path condition computed by COVA, and this path constraint is used to classify the Taint flow later. To give you a better impression of how COVA works, I want to show you an example here. On the right side, you see the code of the Android app. COVA is configured to check the callback onClick and the static field build version SDK int. COVA scans the program and computes a constraint map, which associates the path constraints required to execute each statement. So for example, here this if statement is only reachable when the user performs a click on the UI. To note here that the path constraint COVA computes only considers the APIs which COVA was configured to check. So it is only partial path constraints. Moreover, COVA is publicly available on GitHub, so you are welcome to use it for other purposes. With the help of COVA, we conducted an empirical study on real-world Android applications. For the experiment, we random sampled 2,000 apps from the Android Zoo dataset. These apps were available in popular app stores such as Google's Play Store between 2016 and 2018. And we used the Floudroid version 2.5.1 in its default configuration. Floudroid reported 28,000 Taint flow, more than 28,000. Floudroid reported more than 28,000 Taint flows in these 2,000 apps, and these Taint flows were distributed in 1,022 apps. And we also collected constraint APIs that COVA can check for the three factors we defined: UI interaction, configurations, and I/O operations. The experiment was semi-automated in 2 steps. In the first step, we would like to filter some false positives. Since it is impossible to inspect these more than 28,000 tent flows manually, we conducted a case study of the most common tent flows to filter some false positives. We applied stratified random sampling by dividing the tent flows into groups according to the source sync pair appeared in each tent flow. This table shows you the top 3 groups of interprocedural and interprocedural tent flows respectively. In each group, we sampled 10% of the apps which contain the tent flows with the respective source sync pair. During the manual inspection, we identified a few false positive patterns. Here you see an example of the tent flows from group A and E with the source open connection and the sync set request property. The source method open connection creates a connection object. The sync only sets the general properties of a HTTP request. So this source sync pair combination doesn't constitute a leak, since the connection is not even opened when only calling open connection. One has to call connect or other equivalent method to initiate the communication. So this is a false positive. Another example is the tent flow from group B. For example, here the source is obtain message and the sync is sent message. And it turns out that actually the source obtain message is owning a factory method which creates a new empty message instance. It doesn't return sensitive data. So this is also a false positive. As you have seen these 2 false positive patterns, the root cause here for this false positive is that actually the sources used by Flowdroid is inappropriate. So we examined all 47 sources used by Flowdroid and identified 11 of them are inappropriate and they should be excluded since they cause 28% of the tent flows being false positives. We have reported these findings to the maintainers of Flowdroid and they confirmed the mistakes and removed those sources from Flowdroid's GitHub repository. So the takeaway here is that researchers who use the Flowdroid in the default configuration may need to re-evaluate their conclusions because we already found a few papers in which the work was built on top of Flowdroid and these inappropriate source and syncs were used. Next, I want to show you some false positive pattern which is caused by the analysis rule used in Flowdroid. In this example, Flowdroid tends this secret and reports a data leak when the sync method is called on this. However, in this case, there is actually no tainted data flows into the intent I which passed for the sync method. So this data leak doesn't make any sense here. It turns out that all tent flows with tent connecting sources and syncs on the same object are actually false positives. So for better precision, such rule should not be used for all source and syncs, but only in certain cases. Then we have step 2. After filtering the false positives, we classify the remaining tent flows based on the path constraints computed by COVA. So as an example here, Flowdroid will report that there is a tent flow between source and sync. And COVA is configured with 2 constraint API, getX and getY. GetX returns a configuration option, and getY returns an input from a file. And then we give COVA the source statement and the sync statement. COVA will compute the constraints based on the constraint API for these 2 statements. And the path constraints are X and Y. And then we conjoin them with logical conjunction, so we get the constraint for this data flow, which is x and y. Since x belongs to configuration and y belongs to I/O operation, so this Taint flow is then classified as configuration constraint and I/O constraint. In this way, we could classify the Taint flows reported by flow rate. In step 1, we identified 31% Taint flows being false positive. In step 2, we, with the path constraints computed by COVA, we identified the 0.7% of them are infeasible because the path constraints are equal to false. We also identified that 9.3% Taint flows are only dependent on UI interactions. 2.7% of them are only dependent on configurations, and 0.6% of them are only dependent on I/O operations. And there were also Taint flows which are dependent on multiple factors. As you can see here, the numbers in the intersections are actually quite small. Also, we categorize the rest Taint flows as unconstrained. However, this is only an upper bound since we didn't filter all false positives in step 1, and COVA didn't scale for some of the apps. As we have seen the classification on last slide, Taint flows are really conditioned by combinations of these 3 factors we defined. That we conclude that the most Taint flows could be dynamically confirmed by different tools that specialize on respective category. Thank you for listening. You can find more details about the study in our paper. Feel free to contact me if you have any questions. Bye.